Welcome all. My name is Manoranjan Oja, Assistant Professor, Department of Basic Science, Chemistry, SR University. Today we'll discuss the topic is lithium ion battery materials. So we'll discuss here what is lithium ion battery and what are the materials used for this purpose. So what is the importance of lithium ion battery? If you see, particularly for lithium ion batteries, it is useful in everywhere in our daily life, from starting from the buses or cars or two-wheelers or bike, camera, GPS system, mobiles, which are using every day in our daily life, torch, whatever way if you see, or computer or laptop, these applications of this lithium ion battery is everywhere. Without the use of the lithium ion battery, you cannot think of one day. So it is very essential and very important that how the lithium ion battery works and what are the materials is used for lithium ion batteries. So they are extensively used in consumer electronics and smartphone or electric vehicle or renewable energy storage systems. The propel this why it is so much popular because of its high energy density and long cycle life or lightweight nature and low self-discharge rate. So we'll discuss one by one what is the meaning of those things. But first, whatever meaning is high energy density. So if we think the lead acid battery normally used, which is in bigger size, so their energy density is very low than that of the lithium ion battery. This is an advantage. For imagine that you need to connect one battery to your mobile, that is weight is very much high. So it is not sustainable. So we need some setup or we need some technology which is very lighter and energy density is very high, means we can store much more energy in that small devices which is very lightweight. So that's what two things is coming, that lightweight we need for our daily life portable things that we can carry with us. So that is lightweight nature. And high energy density means that energy can be stored in the device for a large amount, means we can use for a long duration, that is high energy density. And long cycle life means it can run for a long time, means durability or stability is very high. So after maybe 6 months or 8 months, no need to throw. So it will again continue for 1 year, 2 years, 3 years like this. So that is the long cycle life. Self-discharge rate means, let's say we charge a lithium ion battery today, then we didn't use it. We keep it in such that way that that charge it automatically will be discharged or not. Let's say for one mobile we are charging it 100% charge is there. Now we didn't use it anything. We keep it. That if day by day its charge is coming down from 100% to 90%, 95, and 88%, say 87%, 85%, means it is discharging itself. So it is calling self discharge. So we need some battery which is very low self discharge process, means on its own it is not discharging very fast, that is called low self discharge rate. The performance, safety, and lifespan and cost of the lithium-ion batteries are strongly dependent on materials used in their constructions. So, what is the stability or how much star we can store in the device, and what is the cost of the material, or what is the more importantly the safety? How much it is safety or performance? These are depends on which materials we are using in that battery. So this is called the lithium ion battery. This is performance completely depend on the which materials we are going to use it in that battery. Right. And there are different type of the component is the battery, that is called cathode, anode, electrolyte, separator, all those things, current collectors, packaging materials. We'll come to later one by one. The continuous research and development in the battery materials is crucial to improve the energy efficiency and reducing cost, enabling sustainable energy solutions. So what we need, that we need one system which is very energy efficient. Means for charging how much energy we are providing, we can get the same energy or similar energy. So there our efficiency of the device will be much more higher, and easily we can make it large scale, and also cost of the material should be low. So that's then we can use it in everywhere, and economically it will be sustainable. Right, these are the properties it should have. So if you see one battery, that is in this battery, if you see there is many parts of it. So one is called this if it is marked, if you see this is a copper, or this side if you see is the aluminum. The both end side, this if you take it the plus and minus like this. So inside it, so many layers is there. Those materials we are talking about, the different kind of materials is used for the lithium-ion battery. So there will be, we discuss that there is one part is called cathode, another part is called anode, then separator and electrolyte. This is the major part. But this cathode here, one compound is called NCA. It is coated on the aluminum foil. So one foil is there. In that foil, this black color compound is coated. In the similar way, the graphite is coated here in copper side. So this is a current collector. In that current collector, this materials is coated. Then there should be some space between this anode. This is, let's say, graphite is our anode, and this NCA is the cathode. So this anode and cathode, in between there will be one space or one thing that material will use that will separate two things, this anode and cathode. It will block the movement of electron, but it will allow the passage of electrolyte or ions. So that is called separator. So one separator has to be there inside the cathode and anode, and one electrolyte will be there. So electrolyte means salt with solvent. So electrolyte will be there. So these are the major setup or component in the battery. Now if you see how it works for lithium-ion battery principle, you just compare this structure to here. That here if you see this current collector is there, this copper current collector, here the aluminum current collector, these are current collector, right? In that this material is coated, here is this material, this is called graphite, and there this NCA material is coated, or lithium metal oxide some is coated. In between if you see this one is your separator. This separator will allow the ion passage but not the electrons, right? So now let's say what we are doing, we are first discharging it. When you are going to discharge it, then means when we are using the mobile or something, that battery in that when we are using the, or we are consuming the power or energy, then that time how reaction is happening. So this lithium ion, so when it is discharged, so then which side, cathode side, that is where lithium metal oxide is there. So this cathode side we are making minus. So this side is minus, and opposite side it is plus. So this side is plus, and this side is minus, this side. So as it is a minus, so that's why the lithium plus ion will attract this side. It will come this side. And it is plus, this lithium, this electron is giving and coming here. This lithium inside of the compound is giving the electron, and lithium plus is coming this side because this is minus. This is the discharge step. In the charging step, it is totally opposite. So this plus, so cathode, what is the negativity to us? So cathode will be positive here, and this side will be negative here. So now lithium ion will grow from this side to this side. It will move from this side to this side. When this lithium ion is coming and staying inside the molecule, this red color, this is process is called insertion process. And when it is coming back, it is going back, this from this lithium, we call desertion process, deinsertion process, or it is called intercalation or deintercalation. Basically, what is happening? What we are doing, we are making plus or sign minus in the two electrode side. Then lithium ion is coming one side, then again it is going back. So only the movement of lithium ion is taking place during charge and discharge. That's how this reaction is taking place in the lithium ion battery. So these are the, if you see what are the components just we discussed, that we are using that cathode, we are using the anode and electrolyte and separator. So this cathode means is stored lithium ion during the discharge, because it is discharge time we are making a positive negative ion. So lithium plus ion is coming and during the discharge, and opposite way during the charges lithium ion will move or store in this. And electrolyte allows the lithium ion to move from one part to another. So in the medium, only lithium ion is flowing one side to another side. And separator we are using in metal, that it is blocking the short circuit or electronic transitions or electron transformation, or electron cannot flow. So we are blocking the flow of electron. Only ion can flow inside the materials through the separator. So this is separator. Right. So these are the fundamental units or components of the lithium ion battery. So there will be two sides of, you see, there will be anode side and cathode side. So in two sides, cathode material will be different behavior and anode material will be different behavior. So there will be two types of the materials according to the electrode, that one side will be cathode, another side will be anode. And those, what are the, we'll discuss here, what are the cathode material we used in the lithium ion battery. So commonly, one previously from beginning, we use this material called lithium cobalt oxide, or the short name it is called the LCO. LCO or LiCO2, that is called lithium cobalt oxide. This one very widely used for the smartphone or laptops. And the beginning, it was the only lithium ion battery was used. But it is, why it is used? Because it is very high energy density. Means it is very light. We can use it. This is, and energy density is high. The theoretical capacity of this compound is 274. Theoretical capacity means, in theoretically, this LCO how much charge can store. That will say that what is the theoretical capacity of the LCO, that is 274. But practically, when we are making the device, then from there we maximum got 160 milliampere hour per gram. The maximum we can get the practically, or highest in theoretically we can receive 274. But we are not achieving or do not get from the experimental when we do the experimental work. So we receive maximum of 160 milliampere hour per gram. This compound is very limited thermal stability, means during the heating this compound breaks down or sometimes catches the fire. So this is the one red flag for this LCO compound, that is thermally not that much stable, and higher is cost. Because in this compound, if you see cobalt is there, because of the cobalt this cost is very high, because this abundance of the cobalt in the earth crust is very low, and in also in the globally this existence of the cobalt in the form of mineral is not evenly distributed all over the world. So some specific country or region have the source of the cobalt. So that is the problem with the lithium cobalt oxides. So if you see the structures of the lithium cobalt oxide, how it is, so it is called layer type structure. In layer structure, what is happening? This if you see, this is octahedral. In middle there is cobalt, and 6 oxygen atom is coordinated octahedrally, and this is complete making one layer. And that in between two layers there is lithium ion atom. This is the one layer structures, and where one layer is made by COO6, where cobalt is octahedrally coordinated with 6 oxygen atom, and another layer it is lithium can occupy the positions. So that's how the structures of the lithium cobalt oxide. Another compound is very hugely nowadays is used, that is called LFP, or lithium iron phosphate. This compound is very stable in means excellent thermal stable and chemical stable. This is the one advantage of not using the LCO, using the LFP. So because it is stable, very chemically also very stable, and thermal stability is much more higher than LCO. And also long cycle life, means it will run for a long period of time, 2 years, 3 years, 5 years, like this. And high safety, means the safety compared to LCO is much more better for lithium iron phosphate. But what is this compound has a lower energy density than the compared to LCO. So what is meaning? Means this compound is much more heavier than that of lithium cobalt oxide. So as it is size, weight is much more higher. So that's why its energy density is lower than that of LCO. Theoretical capacity for this compound is 170 milliampere hour per gram, but practically what we receive maximum 165 milliampere per hour. It means it is matching the with the theoretical, means maximum how much we can get, that is 170. In practical also we are getting the 165 or close to 170 milliampere hour per gram. Means this material whatever we are using, we are getting the maximum benefit of it. There is no scope of any increment because it reached the maximum value. But in case of the lithium cobalt oxide, maximum it is 274, but we are in the close to little bit more than the halfway, that is 160 milliampere hour per gram. So commercially it is used for in the electrical buses, stationary energy storage. Stationary energy storage, because its energy density is very lower, so that's why if you need the same energy density compared to the LCO, will be lighter than that of LFP. And this structure is called olivine structures. What this material, this PF4, this it make the tetrahedral structures, where iron will be in the octahedral structure surrounded by 6 oxygen atom, whereas phosphorus in a tetrahedral surrounded by 4 oxygen atom, and lithium ion will come in the this size. So it is a combination of octahedral and tetrahedral sites of the iron and the phosphate group respectively. So this type of the structure is called the olivine structures. Another compound is called the lithium manganese oxides. This compound is in advantage is this is lower cost, because if you see here there is no cobalt, so that's why cobalt is not there, means so we are reducing the cost and good safety. But problem is there, it is faster capacity fading, means the stability of the compound is very less. So it is giving satisfied result, safety wise is good, cost is also very less, but energy density is okay in border region or moderate, but its stability means you cannot use for long run, because this compound gets decomposed, or so the structures of the compound distorted, or the stability is not there for very longer run. So that is the disadvantage of the LMO, or lithium manganese oxides. Now come to the compound which is now very rapidly used now for Tesla also is using this compound, that is called NMC. So balanced performance in energy density, safety and lifespan, and widely used in electric vehicle, and reduced cobalt content, lower the cost and environmental impact. So actually what is this NMC compound is similar to LCO what we discussed earlier, that lithium cobalt oxides, where that lithium, some amount of lithium is replaced with nickel and manganese. So what we are doing, what this total in LCO is total cobalt was there. So some amount of the cobalt if we are replacing with nickel and manganese, then what we call the compound nickel manganese cobalt oxides. As we are replacing the cobalt, so its um, cost also we are reducing it. But in the same time, what we are getting energy density is also good, safety wise also good, and lifespan also is good. So we are reducing the cobalt amount, so energy also is cost also reducing. Another compound is called nickel cobalt aluminum oxides. This nickel cobalt aluminum oxide, here also what we are doing, we are replacing this cobalt with some amount of aluminum and nickel. So what the energy density of this compound, if you see this capacity is 180 milliampere hour per gram, and it's also used for high performance electric vehicles as well. And so this compound, this is requires very sophisticated battery management due to the safety concern. There is some safety concern for this materials, because sometimes if people overcharged or overly drained, then there will be safety issues for this compound. Anode material, these are the cathode material we talked about it. Now, what is the anode material it is used for? A anode is responsible for the storing lithium ion during the charging. Anode materials greatly affect the battery's charging speed and durability. So means one side the cathode material we used, that is in cathode side, another material we are using in the anode side. This making this more we used or very widely it is used is graphite. Graphite is a graphene layer stacked together, that is called graphite. So this graphene layer, this distance between two layer, it is 355 picometer, and it is hexagonal crystal structures. This is commonly used for the anode material in lithium-ion battery because it is very low cost and reliable and stable. So if you see there is a gap between two layers, and lithium-ion come and can sit into this layer. So that's how intercalation or de-intercalation takes place in the lithium. Another material is used called hard carbon, but this is very rarely used in the lithium-ion battery, but it is mostly used in the sodium-ion batteries. So what is that hard carbon is? For this, when this, if you represent every planar, this one as a graphene, then this layer, if it is making this one by one, it is arranged in a proper way, stacked one by one, then we call this the graphite. But if this graphite orientation is different direction, then you won't get in a particular directions. All our graphite is not in the same direction, it is arranged. So there is disorder of the materials is there. Due to the disorder of the materials, what are the properties of the carbon, we call it as a hard carbon. So hard carbon is that it is a graphite type compound, but it is in disorder in nature. So this is called the hard carbon. So it is normally used as a widely used as anode material in the sodium ion battery, not lithium ion battery. Another anode material which is called LTO, that is called lithium titanate oxide or lithium titanate or titanium oxide. This Li4Ti5O12. This is, if you see, this is spinal type structures. It is extremely long cycle life, means its stability is very good. There is no distortions or property or structural deformations of the compound when you long run. It is also for excellent safety and fast charging and discharging. So you can charge this material very fast. That is called C rate. C rate is very high. So means you can charge this using this material in the battery very fastly, charge and discharge. But problem here is that its energy density is very low. So 175 milliampere hour per gram capacity this is. So energy density of this material is low. This is the one disadvantage of this compound. Silicon based anode also is being used. This most important is that the silicon, why silicon everybody is focusing is because theoretical capacity of the silicon is 3580 milliampere hour per gram. So if you compare with this one as a graphite or hard carbon, that is close to 275 or 300 milliampere per gram, which is this compound is 10 times higher. But this is the good advantage of the using the silicon based anode material. But problem is there will be a during charge and discharge or lithium ion desertion and insertion process, there is a volume change or expansion of the compound during cycling charge and discharge. Because of this one, the stability compound is very less. That's why after few cycles running, this compound performance decay very badly. That's what is the problem using of lithium based anode material. So so that's why ongoing research is aimed to improve the durability. If we are able to solve the expansion issue or stability of the material, silicon based anode material, then it will be a very good achievement for this anode material in the lithium ion battery. Now, cathode material we have discussed, anode material we have discussed. Now we are discussing that electrolyte was the material is used in between, which is responsible, so will take care of the movement of ions. So normally for lithium ion battery, this called PF6, that is called lithium hexafluorophosphate is used as a salt, and the solvent is used called PC and EC, PC, DEC, like this solvent in the mixer 1:1 or different ratio it is used. So liquid electrolyte, what we used, that we used a sodium salt that is normally for LiPF6. With that solvent, carbonate based solvent we used, that is for propylene carbonate, ethylene carbonate, this type of the compound we used, which very ionic, very high ionic conductivity and flammability possesses safety risk. Here in liquid electrolyte, what is the disadvantage is that it can catches fire very rapidly or very easily. So this is the disadvantage of using the liquid electrolyte. So if you use the solid electrolyte, the advantage is that this leakage problem or catching fire catching problem will be somewhat restricted, or it will be less. But this conductivity of the materials is very low. So ionic conductivity of the material is very low. This is the advantage of using the solid electrolyte. So that's why the performance is decreases. So if we are able to find out some solid electrolyte where the conductivity is much more higher, and then that will be excellent for safety wise and also for commercial use for the solid lithium ion battery. And sometimes what we do normally, we can use the gel polymer electrode. Some polymer can be made a gel, and that can be used in the as a gel polymer electrolyte. So what is the advantage that in liquid electrolyte there will be some leakage or catching fire issues, but in gel polymer that problem also somehow it can be somewhat amount can be reduced using the gel polymer electrolyte. Separator in between, which are separating for the cathode and anode, this is called separator. So there is different kind of a polymer is used. There is a polyethylene triple layer or polyethylene propylene PP, it is called polypropylene, or multi-layer PP or PEE combinations also used. Sometimes triple layer of polyethylene polypropylene, this is also used as a widely used as a separator for lithium ion battery. So what we need for this separator, it will restrict direct contact of the anode and cathode so that electron cannot flow, but it will allow the passage of the electrolyte. So that's where we need, and it also can sustain with high temperature, so that this device cannot cross it, or some safety issues will be maintained. Current collector, where the material is coated, that we call the current collector. So this normally different kind of material is used. Copper material, copper foil or aluminum foil is used for these purposes. The binder and conductive additives for when we are making the slurry or coating the cathode material or anode material. What we do, we took the cathode material, then we added some compound, white color powder compound, that is called PVDF, polyvinylidene dichloride. So we added that powder. Then to increase the conductivity or make the slurry good, we used carbon black, and then we make a paste it. Then we coat it on the this current character. So environmental and sustainability aspects of the lithium-ion battery. So in lithium-ion battery we use the lithium, cobalt, nickel, but cobalt is very means the environmentally it is not a good element, and there this scarcity is there for in cobalt health wise issues is there for cobalt, and for mining for lithium that it also not a good environmentally it is not a benign process. So this is the two problem with remains for cobalt and lithium. So and also that distributions of the lithium also all over the world is not evenly. So in some country or some region is have a source of the lithium, or they have a in deposit of lithium. That's why there is a supply issue for the lithium cobalt as well. So this is also it may supply chain will break, then there will be issues in the using for lithium ion battery. So a consumer cannot get this materials or battery which is used for the daily life. So this supply chain can be broken at any point of time, because it is some specific region, some few part of the world having the reach of lithium and cobalt, and they can restrict it to make this thing ours happen. So this is the problem with the lithium and cobalt, that the supply chain will break, and then consumer can face the problem. And cycling challenges due to the complex material composition. So cycling challenges is there. So now people are focusing on that this used lithium ion battery, how can we recycle it and use it. So the best possible way is that no need to use the lithium, and in case of lithium we can use different metal like the sodium or some other metal ions, and also it should be cobalt free cathode. If it is cobalt free and also recycling technologies are developed, then it will immensely help to the society environmental way and sustainability aspects as well. So future trend is the development of solid state battery, where the leakage of the electrolyte cannot happen, and stability and safety wise it will be much more better than that of liquid or polymer gel based electrolyte. And use of the silicon anode, where the performance will be 10 times, at least 10 times higher than that of the carbon used. And also cobalt free and low nickel cathode will be excellent for the future aspects. These are the advantage future trend that we can look for the to make the lithium better lithium ion battery. So we have discussed here how the lithium ion battery works, what is the mechanism, which materials is used for cathode material, anode material, and electrolyte what are the use, and separator what is the use, and what is the purposes it is being used, and also what is the future, what we can think about the lithium ion battery. Okay, so we'll stop here in this topic. We'll continue the next time.